Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today we're diving deep into the fascinating world of gradient descent optimization algorithms, a topic that's crucial for anyone working with neural networks. Get ready for some serious tech talk.
I'm pumped. Gradient descent. It's the backbone of so much deep learning, right? So let's start with the basics. What are the main variants we need to know?
Absolutely. We've got three primary variants: batch, stochastic, and mini-batch gradient descent. Batch uses the entire dataset for each gradient calculation. Incredibly accurate, but painfully slow for large datasets. Think of it as meticulously surveying the whole terrain before taking a single step.
Right, a very thorough but slow approach. Then stochastic is the opposite?
Precisely. Stochastic updates parameters after each training example. It's super fast, but the updates are noisy, leading to a lot of fluctuation. Imagine a frantic hiker constantly adjusting their path based on each tiny rock they encounter.
So mini-batch is the happy medium, right? A compromise between speed and accuracy?
Exactly. Mini-batch uses small batches of data for each update. It balances the speed of stochastic with the stability of batch. It's the Goldilocks method, just right for most deep learning tasks. It's the workhorse of modern deep learning.
I see. So what are some of the challenges we face even with mini-batch? I mean, it's not a perfect solution, is it?
No, not at all. One major challenge is choosing the learning rate. Too small, and convergence is agonizingly slow. Too large, and the algorithm bounces around the minimum without settling. Then there's the issue of the learning rate being uniform across all parameters. What if some parameters need bigger adjustments than others?
That makes sense. Different parameters, different needs. So how do we address these challenges? This is where the advanced optimization algorithms come in, right?
You got it. That's where things get really interesting. We have algorithms like momentum, which adds a fraction of the previous update vector to the current one, smoothing out oscillations and speeding up convergence. Think of it like a ball rolling downhill. It gains momentum.
Momentum. I get that analogy. It's intuitive. What about Nesterov accelerated gradient, NAG?
NAG is a clever improvement on momentum. Instead of blindly following the current gradient, it looks ahead, anticipating the next position of the parameters. It's like a smart ball that anticipates the terrain ahead and adjusts its speed accordingly. Much more efficient.
Interesting. And then we have the adaptive learning rate methods, right? Like ADAGRAD, ADELTA, RMS-prop, and ATOM.
Yes. These are game changers. ADAGRAD adapts the learning rate for each parameter based on past gradients. It's great for sparse data, but its learning rate can shrink too aggressively. ADELTA and RMS-prop address this issue by limiting the window of past gradients considered. ATOM combines the best of both worlds, adaptive learning rates and momentum, and is often the go-to choice.
So many algorithms. And then there's ATOMAX and NATOM. How do they fit in?
ATOMAX is a generalization of ATOM, using the L-infinity norm instead of the L2 norm for gradient scaling. It's more numerically stable. Now, NATOM incorporates Nesterov momentum into ATOM, giving it even faster convergence. It's like adding a turbocharger to an already powerful engine.
Wow. And AMS-GRAD? I've heard that one mentioned.
AMS-GRAD addresses a potential issue with ATOM's convergence in some cases. Instead of using an exponential moving average of past squared gradients, it uses the maximum, ensuring a non-increasing step size. It's a refinement, but its overall superiority over ATOM is still debated.
So much to consider. What about parallelization and distribution? How do we speed things up even more?
Excellent point. For massive datasets, we need to parallelize. Techniques like hog-wild, downpour SGD, and elastic averaging SGD offer different approaches to distributing the computational load across multiple processors or machines. TensorFlow is a powerful framework that facilitates this.
And finally, what are some additional strategies we can use to optimize SGD?
Good question. Shuffling data, using curriculum learning, batch normalization, early stopping, and even adding gradient noise can all significantly improve training. It's a whole ecosystem of techniques.
This has been an amazing overview. It's clear that choosing the right optimization algorithm is crucial for success in deep learning. Thanks for breaking it all down.
My pleasure. Remember, the best algorithm depends on your specific dataset and model. Experimentation is key. And that's all the time we have for today's Tech Bytes and News. Thanks for tuning in, and we'll catch you next time. Goodbye.
Bye-bye.